Alright guys, we are going to start on chapter 12. Can't even spell chapter. Alright, chapter 12 is liquids, solids, and intermolecular forces. So let's first talk about intermolecular forces. And I will refer to them as IMFs. Okay. So it's important to realize, first of all, that intermolecular forces are very weak attractions. And just because they're weak doesn't mean they're unimportant, but they're weak attractions between molecules. So if you think about the game Red Rover, and hopefully you guys played that when you were in school. They have since banned it at my kid's school. That and tag, and I think anything else that's fun. Okay, but you know they're not exactly going to school right now, so what difference does it make? So think about Red Rover. You know, you're holding hands with the person next to you, and you say Red Rover, send the weakest, smallest person right over, and the person from the other team has to run over and try and break through your hands. Okay. And if they break through, they go back to their team. If they don't break through, they stay on your team. Person with all the people wins, right? So if you say Red Rover, send the weakest, smallest person right over, you keep them. Now, when you get down to the very last person on the other team, it's probably the biggest, strongest kid on the playground, and he comes charging at you, you remember? And all of a sudden, he bursts through the line, and instead of breaking your hands apart, he just rips someone's arm right off at the shoulder. You guys ever remember that happening in elementary school? Okay. Of course not, because if you are the molecules, all the kids on the playground are the molecules, holding hands is like an intermolecular force. Okay, it's relatively weak compared to, you know, your arm stuck, being connected to your body, as it were. So the intermolecular force is like holding hands, or another way you can think of it is as not holding hands, but Velcro. So it's relatively weak, but it is important. And these are also called, we'll say they're also known as van der Waals forces. So sometimes you'll hear people refer to van der Waals forces instead of intermolecular forces. Those terms are used interchangeably. And if that word van der Waals, or that name sounds familiar, that's when we talked about real gases. The ideal gas law becomes the van der Waals equation when we take into account real gases. Okay, so let's talk about our first intermolecular force, which is London dispersion forces. And I will generally refer to them as LDF. Okay, your book just calls them dispersion forces. They also refer to them as London forces. I just learned them as London dispersion forces, so that's what I'm going to call them. It doesn't really matter what we call them. But these are the weakest intermolecular force of all the intermolecular forces, and we'll talk about 4 of them. Okay, weakest intermolecular force, and they come about due to a weak attraction due to shifting electron cloud. Okay, so let's see what that looks like. I'm just going to draw a really, really simple diagram. Ooh, allergies are getting to me. So here's 2 helium atoms, all right? And around each helium atom is a more or less symmetrical electron cloud, okay? And that electron cloud Remember, the electrons are always moving. Really, we don't actually know where they are, but we approximate them as a sphere. So let's just say for some reason the electrons on one molecule kind of shift, and let's just say the electrons on this molecule just kind of shift in that direction. So what we'll get is a helium atom with this kind of distorted electron cloud kind of poking out one way, and the nucleus is more to one side. Well, guess what? Electrons repel each other, so the same kind of shift is induced in the other helium atom. Okay, so now we have asymmetrical electron clouds. So that means this side, the nucleus is closer, so it's a little bit positive. This side's a little bit negative, makes this side a little bit positive, and this side a little bit negative. Remember, those are the partial charges. Those guys are all partial charges, partial positive, partial negative, meaning it's not fully ionized, it's just a little bit positive or a little bit negative on one side or the other. Well, is this going to stay like this? No, not necessarily, because the same thing can happen in reverse. And again, we don't really worry about why, just knowing that electrons can always move. The electrons can shift in this direction. And they can shift in any direction. It doesn't have to be just left to right, obviously. So now we have partial positive, partial negative, partial positive, partial negative. Okay? And because those electrons are always moving, that's what makes it weak. Because then they could just go, right back to being not shifted. And they're always just going to be constantly moving. So that's what makes it a very weak force. So where do we see this? Okay. This is seen in all molecules and atoms. Why is it seen in all molecules and atoms? Because all molecules and atoms have electrons. If there's an electron cloud, it can shift. Okay, but it's the only intermolecular force for non-polar molecules and atoms. And when I say atoms, really the only atoms we're talking about are noble gases. Okay, so just some examples. This is not by any means an exhaustive list, okay, but CH4, remember a carbon-hydrogen bond is a nonpolar bond, okay? So anytime you see just carbon and hydrogen, that's going to be nonpolar. London dispersion forces are important. Something like CCl4, carbon tetrachloride, that's symmetrical, okay? If it's symmetrical, it's nonpolar. Diatomics, F2, Cl2, whatever, they are nonpolar as well because they are symmetrical. And then noble gases, neon, argon, helium obviously up there. Okay, so that is London dispersion forces. In the next video, I'll talk about how we can affect those London dispersion forces.